Integration is a fundamental operation in calculus, and is probably one of the first things you learn about in a course on the subject. One great thing about real definite integrals is that they have a very nice geometric interpretation. That is, the signed area between a curve and the x-axis in R2, which any math student will recognize. But what about an integral over the complex numbers? Is there any geometric interpretation here? In this video, I hope to demystify complex integration a little bit for you. The first idea to go over is that of a vector field. In the complex plane, we can represent any complex number as a vector. Writing a complex number in exponential form allows us to quickly determine the angle the complex number makes with the real axis in the plane, as well as the absolute value of the complex number. Now suppose we have a function f of z. For example, say f of z is equal to 1 over z. If we take any complex number z as our input, we get a new complex number back. And we can again think of this output number as a vector. Evaluating f of z at 1 plus I, we get 1/2 times 1 minus I, a vector pointing into the fourth quadrant of the complex plane. Now, imagine translating the tail of this output vector to our input point 1 plus I. This is the vector we want to see in our vector field. If we then do this with every output vector for our function, we can look directly at our input point on the plane and see that the vector emanating from it captures the phase and the modulus of f of z at that point. The idea of two-dimensional work and flux is pretty straightforward. Suppose we have two vectors a and b. We can define work simply as the dot product of these two vectors, which is the absolute value of a multiplied with the absolute value of b, all multiplied by the cosine of the angle theta between these two vectors. When the angle between a and b becomes smaller, cosine of theta approaches 1, and the absolute value of the dot product in turn becomes larger. If the angle between a and b gets closer to 90 degrees, cosine of theta approaches 0, and thus the absolute value of the dot product becomes smaller. Flux can be defined as the dot product between vector b and a 90-degree rotation of vector a. In other words, the absolute value of a multiplied with the absolute value of b, all multiplied by negative sine of the angle between these two vectors. When the angle between a and b is smaller, sine of theta is smaller, and in turn the absolute value of the flux becomes smaller. If the angle between a and b approaches 90 degrees, sine of theta approaches 1, and thus the flux becomes larger. The absolute value of the flux between two vectors is largest when the vectors are perpendicular. Work is negative when the angle between the two vectors is obtuse, that is, whenever cosine is negative, and flux is negative depending on whether vector b is to the right or left of vector a. If we're facing the direction of vector a, then flux is negative if vector b is to our left. Let's say we have a vector field given by a function f of z and some contour we want to integrate over. Now consider the integrand of our complex integral, f of z times dz. At any given point z in the vector field, we know that f of z and dz are both complex numbers. F of z is simply the function in question, and dz represents an infinitesimally small change along our input curve in the complex plane. As complex numbers, we can represent f of z and dz as vectors in the plane. dz is an infinitesimally small tangent vector on our contour, and it points in the direction we are integrating. Obviously, the direction of f of z depends on what our function is. What we know is that when multiplying two complex numbers, we add together both of their phases and multiply their moduli. Thinking of the complex numbers as vectors, this simply means that we add the angles of the two vectors together and multiply their length. Writing our integrand in exponential form and expanding using Euler's formula, what we ultimately find is that our integrand is equal to cosine of theta plus I sine of theta times the magnitude of the vector f of z times the magnitude of the vector dz. But now it's clear that this is exactly the work and flux of two vectors. The problem is, when we look at our vector field, we see the angle between f of z and dz. Notice, however, that the angle in our integrand is not the one between the vectors of dz and f of z. Instead, the angle we want is the phase of f of z added to the phase of dz. It looks like our vector field doesn't depict the angles we're looking for. To see how we can fix this problem, consider a point on our contour. Let's also use coordinate axes to make visualization easier. At this point on the contour, the tangent vector dz points toward the second quadrant of the plane, and the vector field is flowing towards the third quadrant. With the axes, we can see that dz makes an angle alpha with the real axis, and thus has a phase of alpha. F of z, on the other hand, makes an angle beta with the real axis. Let's focus only on these angles for a moment. It will also be helpful to represent angles only in the range of minus pi over 2 to pi over 2, so I'll move beta down here. Now, take a look at the angle alpha plus beta, pictured here in green. Alpha looks to be close to 135 degrees, and beta appears to be about minus 170 degrees, so alpha plus beta is somewhere around minus 35 degrees. This is the angle in our integrand, the one we want to visualize. There's a clever trick we can apply here that will give us a way to visualize this angle in our vector field. We have to take the complex conjugate of our function vector f of z at this point. This new vector, f of z conjugate, clearly has phase minus beta, so the angle that f of z conjugate makes with the real axis is minus beta. But now, if we look between this vector and our dz vector, it's immediately obvious that theta, the angle we were looking for, is equal to alpha minus the phase of f of z conjugate, that is, alpha minus negative beta, or alpha plus beta. This will work regardless of the phase of either f of z or dz. Now, imagine that we apply this procedure to every vector in our vector field. Instead of just plotting f of z, we plot f of z conjugate. What we end up with is a vector field in which we can actually visualize the angle in the integrand at every point along our contour. The vectors in the vector field always make an angle alpha plus beta with the vector tangent to the path of integration, where alpha is the phase of our infinitesimally small tangent vector dz, and beta is the phase of f of z. This vector field, depicting the conjugate of the function, is called a Polya vector field. What we see now is that the work along our contour, that is, how much the Polya vector field flows along with our path of integration, determines the real component of our complex integral, and that the flux along our contour, how much the Polya vector field flows through our path of integration, determines the imaginary component, as the flux is multiplied by I in the integrand, which we can pull out as a constant. What's great about the Polya vector field is that it allows us to roughly estimate the value of a complex contour integral simply by looking at our path of integration in the complex plane, just as we could analogously estimate the value of a one-dimensional real integral in R2 by looking at the signed area between a curve and the input axis. If we now look at the Polya vector field for the function 1 over z, it becomes obvious why the counterclockwise integral along a simply closed contour that contains the point 0 is equal to 2 pi I. Everywhere along the contour, the vector field vectors are completely perpendicular to the tangent vectors of the curve. Thus, the integral is purely imaginary, and is equal to the length of the curve, which is just the circumference of the circle, multiplied by the average magnitude of all the field vectors along the curve.